In this video, we'll be covering the first derivative test. Now, the first derivative test specifically identifies where the local maximums or local minimums of a graph might occur. This is specifically using the first derivative. So, in this first example, we're going to go ahead and take the first derivative so we can view exactly where the local minimums or maximums might occur. So the first derivative of this particular function is 3x squared minus 12. In that case, if I set it equal to 0 and find my critical points, again, or the cases where the derivative does not exist, so I'm going to go ahead and find my critical points, being again f prime d and e, or this is the first derivative equaling to 0. Again, we're going to keep doing that exact same thing over and over and over again. So in this case right here, if I set this derivative equal to 0, because notice it is a polynomial function and therefore doesn't have any issues with it not existing, again, always check that case just to be safe, I'm going to end up with x squared is equal to a positive 12 over 3, which gives me x is equal to plus or minus 2. So that provides me with two potential critical points, two potential locations where there could be a maximum or a minimum. Now, how can we be certain whether or not these locations are a maximum or minimum? Well, I'm going to go ahead and return to the concept that we did in the increasing-decreasing section, where we identified the locations where the derivative was equal to 0 or where the derivative didn't exist. Then we're going to go ahead and identify test value points, and we're going to check whether or not the first derivative is positive or negative to determine what the function is doing in those locations. So I'm going to go ahead and identify all these intervals just to be safe. And then we're going to go ahead and test these values, again, on the original first derivative. So in this function right here, the test value I can pick for this one is 0, this one is negative 3, and this one is positive 3. I'm going to pick 0 first just because it's easier at this point. If I plug in 0 to this function, I'm going to get negative 12, which means my derivative is negative, and therefore my function is decreasing. Negative 3, when I plug that in, I'm going to get a negative 3 times negative 3 is a positive 9. 9 times 3 is 27. 27 minus 12 is definitely a positive number. And the same goes for a positive 3. So you'll notice that I have increasing, decreasing, and then so on and so forth. Now, if I look to what the graph is going to do, you'll notice it's supposed to go up, then down, then up. Again, notice in this particular example, I did not look at concavity, so I don't know exactly how this graph is going to behave in terms of concave up and concave down, but I do know that this function is increasing, then decreasing, then increasing again. So logically, this cubic should look something like this to some extent, which would tell me right here, notice, it's changing from decreasing to increasing, should be a local minimum. And this point right here, notice it's going from increasing to decreasing, should be a local maximum. So that's what we should be able to identify. First off is that there is a local max at the x value of a negative 2, and there is a local min at the x value of 2. The last piece I need to worry about is, well, what's the y value? What is the actual maximum? And what is the actual minimum? These are only the x values, which means that they're only the locations at which those minimums and maximums occur. How do I find out what the max is? Well, I'm going to go ahead and just simply plug in negative 2 to my original function. Meaning I'm going to have a negative 8, looks like plus 24, negative 8 plus 24 minus 5. In which case I'm going to have a minus 13 plus 24, which looks like a positive 11. So 11 is the actual value of that maximum. And if I go ahead and plug in 2, I'm going to get a positive 8, a negative 24, positive 8, a negative 24, and a minus 5. So it looks like negative 29 plus 8, which ends up being a negative 21. So f of 2, which is the value, again, one more time, is a negative 21. So therefore, using the first derivative test, again, this is what the first derivative test is. It says, based on the function's increasing and decreasing patterns, based on the derivative changing from positive to negative, is a maximum, changing from negative to positive is a minimum. And again, that should make sense based on this image right here of how this graph appears. Keep in mind, you need to plug in the negative 2 and the positive 2, the critical points, into the original function to determine the y value. If you can't plug in negative 2 or 2, then that value doesn't exist, and therefore it doesn't actually have a max or a min at that point. But in this case, we have a local maximum at x equals negative 2 for the value of 11, and a local minimum at the x value of x equals 2 for a y value of negative 21.